So, two things I wanted to bring to your attention here. Firstly, if we go right back to where we derived our expressions, we said we would start our timing here. Now, it's because we started our timing here that we ended up with a cause expression. If we had started our timing here, then when t equals 0, x equals 0, our displacement from our equilibrium position, and so we'd have got a sign expression, or if it had been going down from here, it would have been a minus sign. So the point I'm making is that when you look at textbooks online, that sort of thing, you might well find expressions x equals a sine omega t, or x equals minus a sine omega t. That's just about the starting position. If you started here, you'd have a minus cos. So I just wanted to make the point that the expression you get depends on your starting conditions here. So don't panic if you're looking at another textbook or whatever and seeing a different expression. The reason you have that different expression is because you had a different set of starting conditions. Starting here, you get this. Starting here, the cause would be a sine. If it was going down, it would be a minus sign. And if you start here, then it's a minus cos as it goes up. So I just wanted to make that point to you. And that links into what I'm saying here quite briefly about the graphs of these different functions. So if we start with x equals a cos omega t, there's our x. When t equals 0, our displacement is the amplitude. If you remember back here, we said we're going to start our timing at this point, and at t equal to 0, our particle is at its maximum displacement, its amplitude, from the equilibrium or rest position here. Of course, in this case, it isn't a rest position, it's an equilibrium position, because it isn't stopped here. So there's our expression, our graph rather, for a cos omega t. And if you look mathematically, the velocity is the first derivative with time of the displacement, the rate of change of the displacement. If you differentiate that, you'll get minus a omega sine omega t. You don't have to know how to do that, or even that that is the case, but you should know that the velocity is the rate of change of the displacement. That's almost GCSE, although it isn't expressed in those terms. But if you remember, the gradient of a displacement time graph is the velocity. So what you're doing here is plotting the gradient of this graph. So the red one, the velocity, is the gradient of this graph. And it's a minus sign. Now, if you think about that, if x is plus a at this point, this is our positive direction. But at this point, the velocity is in this direction, so it's going to be minus. And at this point, the velocity is a 0. And at this point, it's going to be moving as fast as it can. So that makes perfect sense from an observational point of view, that you would have 0 velocity at this point, a maximum velocity when the displacement is 0, 0 when the displacement is a maximum, and so on. And the minus gives you the direction of that velocity. And then, by definition, the acceleration is minus omega squared x. It is, of course, the rate of change of the velocity. If you differentiate this expression here, you'll get minus a omega squared cos omega t, which is omega squared times minus a cos omega t, which is minus omega squared x. So here we have minus a omega squared times cos omega t. So it's a minus, it starts down here. So at this point, the acceleration is negative. So here it is. And it's a maximum, if you think about it. Here, it is accelerating in this direction. And it's going from going in this direction to going in this direction. So you'd expect the acceleration to be a maximum. And so it is. So there you have the graph of the acceleration against time. Now, the maximum values are going to be different. It's only where A and omega are 1 that they're going to be the same, right? So I have tried to make all of the maxima different. The maximum for displacement, the maximum for the velocity, and the maximum for the acceleration. I tried to make them different. So there you have your displacement, your velocity, and your acceleration graphically.